Now I will say that about the ferrimagnetism. Ferrimagnetism spin alignment is spin up, down, up, down, up, down like this, and it is antiferromagnetic interaction, but the magnetic moment for spin up sublattice and spin down sublattice magnetization is different. And in phenomenologically, it is similar to the ferromagnetism. In that there is a spontaneous magnetization, and also self-saturated domains, and there is a magnetic hysteresis and magnetic saturation. And also at high temperature, there is a paramagnetic behavior. Above Tc. And actually, the different thing is that the differences is that they do not follow the Curie-Bayes law. Curie-Bayes law, and interaction is antiferromagnetic interaction. And when we measure the magnetization versus temperature, T of Tc and M over Ms, and here, there is a spontaneous magnetization in ferromagnet, but in ferrimagnet also there is a spontaneous magnetization, but it is a little bit different, and it is ferrimagnet. Therefore, it is a little bit difficult to conceive what is a ferrimagnet, what is a ferromagnet in the empty curve. But when we write down as magnetic susceptibility versus T over Tc and 1 over chi, and Curie-Bayes law follows that like this, it is paramagnet, and ferromagnet like this, But in ferrimagnet, it do not follow the Curie-Bayes law, and also in like this, it is a ferrimagnet. Why it does not follow the ferrimagnet, we will see that in detail. And anyway, but all of the data, all of the material that exhibiting this kind of behavior, far from the Curie-Bayes law, is not a ferrimagnet, because in some cases the magnetic susceptibility C over T plus zeta, but there is another contribution. Another contribution may come from the various examples. One is the diamagnetism or the paramagnetism, and paramagnetism like Pauli paramagnetism, and Van Vleck paramagnetism, and Landau diamagnetism, and so many additional contributions can be exist. Therefore, when you decide that it is ferrimagnetism or not, and we should analyze the possible scenario, and like a physical interpretation, more in-depth physical interpretation is needed. And also in some cases, there is a neutron diffraction to identify the spin structure is more direct, powerful tool to identify the spin structure. And also, in here, let's consider for the negative exchange energy and the different spin sublattice, and A spin or the B spin, and also M sublattice magnetization is different from the B lattice sublattice magnetization, and because the net magnetization is not zero at low temperature, that's why it shows that saturation magnetization and magnetic hysteresis. And the example of ferrimagnet is that spinel structure. For example, mangan oxide, not mangan, metallic oxide, iron 2O3. Here is M is that zinc or cadmium. In this case, that metallic side is a 2 plus. It is we call it A side, and iron is 3 plus. It is B side. The iron is the ferromagnetic interaction. In the metallic side is the antiferromagnetic interaction, and the inverse spinel. Inverse spinel structure like a Mag4-3 structure. Here is that M is that Fe cobalt nickel, and also A side is the Fe3 plus, and B side is the M2 plus or the Fe3 plus mixing. And the inverse spinel structure, and also mixed ferrite. For example, nickel oxide, iron 2O3 plus zinc oxide, iron 2O3. This kind of mixed ferrite, nickel and zinc dot oxide, iron 2O3, it is a mixed ferrite, also exhibits a ferrimagnet. And from the molecular field theory, most ferrimagnets have low electrical conductivity, and because of the mixed balance in antiferromagnetic interaction, and from the Hund coupling do not favor for the conduction electrons and the hopping of electron one side to other side. And also orbital moments are completely quenched, and also therefore, in order to calculate this, let's consider for the molecular field theory. And let's define that there are A sublattice and B sublattice. In between the A sublattice and B sublattice, there are interaction, and the interaction between A sublattice and B sublattice, gamma AA, and B sublattice interaction, gamma BB, and A sublattice B sublattice interaction, gamma AB. Let's define that there are interaction, and also let's define that lambda A is the fraction on A side, and the lambda B is a fraction on B side. Basically lambda A plus lambda B should be 1. Let's define the lambda mu A or the mu B are the average magnetic moment then the total magnetization should be the sum of the M sublattice to the B sublattice, and it is, in other words, is lambda A Ma. Small a means that A side single magnetic ion. And here lambda B MB. Small index, small subindex is the small single ion. And the molecular field at molecular field for A sublattice is that for A sublattice molecular field is coming from the magnetization B and also interaction gamma AB and the minus and the plus gamma AA MA. It is interaction between the A sublattice. And the molecular field at the B site is that the B side molecular field is coming from the A side magnetization and the gamma AB and the minus and the plus gamma BB and B. There are two molecular fields, and also to simplify this equation, let's define some parameter. Alpha is that gamma AA over gamma AB, and the beta is that gamma BB over gamma AB. Then this molecular field A is that gamma AB. Let's retract gamma AB, then the alpha lambda A MA minus lambda B MB. Molecular field at B site is that gamma AB, then beta lambda B MB minus lambda A MA. Therefore, let's consider for the temperature. T is greater than Tc case, and basically it is MT is that rho C HT. HT means the total magnetic field, and C is the Curie constant, rho is the volume fraction, and for each sublattice. Then therefore MAT is that rho C H plus. H is applying magnetic field. H is that molecular field. MBT or rho C over H plus H MB. And there are several equations. This is first equation and the second equation, and also second equation here. And the magnetization and also molecular field. And we can summarize by tedious calculation. M over rho H can be write down. It is a tedious complication. A little bit complicated. In the CT minus gamma AB. I do not calculate in detail. It is a homework by yourself. Rho C square lambda A lambda B and 2 plus alpha plus beta over T square minus gamma AB rho CT alpha lambda A plus beta lambda B plus gamma AA square rho square C square lambda A lambda B alpha beta minus 1. Yes, so complicated. Therefore, when we write down as inverse chi, then T over C plus 1 over chi 0 term minus B over T minus zeta. It is complicated. In other words, it is that T plus C plus chi 0 minus T minus zeta B. This term can be negligible at high temperature. And anyway, and that's why the reason why it does not follow the Curie-Weiss law. Okay, and you can write down also below TC second. The net magnetization is that the differences between the A sublattice and B sublattice, and therefore MA over M0A is the Brillouin function as a function of J and A prime. It is that it is not simply calculated anyway. Anyway, it is a function of the mu B molecular field KBT. Therefore, in experiments and for the one-of-a-kind calculation of T, basically it is antiferromagnetic interaction, and here is the antiferromagnetic interaction. It's minus C of chi 0. But in ferrimagnetic case, and here like this, it's eta P. And also the magnetization behavior M over MS. Then in conventional antiferromagnet, spin up sublattice and spin down sublattice had this positive and negative magnetization, and that cancel with each other. But in a ferrimagnet, there is a spontaneous magnetization. Therefore, like this, it is a ferrimagnet. It is a spin sublattice and spin sublattice. But the ferrimagnet is there is a spontaneous magnetization, and that's why when we consider for the ferrimagnetism, if we prove that, if we think that it is not a additional contribution like Landau diamagnetism, Pauli paramagnetism, or the Van Vleck paramagnetism, then we can say that it is ferrimagnetism. Then ferrimagnetism also should be investigated as exact neutron diffraction, and therefore the antiferromagnetic interaction and the magnetic behavior similar to the ferromagnetic interaction, but do not follow the Curie-Weiss law. That we can conclude that it is a ferrimagnetic materials. Okay.